Hello and welcome to Chapter 11 Mathematics and the Arts. We're going to talk about Unit 11B, Perspective and Symmetry. Now, visual arts, right? There's at least three aspects of the visual arts that relate directly to mathematics. We're going to talk about perspective, then we'll talk about symmetry, and then we'll talk a little bit about proportion. All right. So let's look at a hallway. All right, this is a side view of a hallway. You have the top of the wall furthest from you, the top of the wall closest to you, the bottom, the floor edge, right, where the floor meets the far wall, where the floor meets. So this line 1, line 2, line 3, line 4, these are the lines, the outside edges of where the hallway walls meet the floor and the ceiling. We have our canvas, right? Here's our little image of our vase. And we have this P, all right? And the artist's eye looking at all of these things. Let's talk about it. So this P1, P2, the various things, this is the vanishing point. The vanishing point is what everything kind of tends to. Notice that even though on the side view, L3, L4, L1, L2, those lines in a hallway, they're all parallel, right? But if you look down a super long hallway, they'll all come to a point, the vanishing point. In order to get your squares, wow, that was a hard one. In order to get your squares correct, we have vanishing points still on the same horizon line, but outside of the image to kind of keep a uniformness to help us in drawing these. An artist's view of the hallway showing perspectives, lines L1, L2, L3, and L4, which are parallel in the actual scene, are not parallel in the painting, as we mentioned. All right, lines that are parallel in the actual scene but not parallel in the painting meet at a single point P called the principal vanishing point. All lines that are parallel in the real scene and perpendicular to the canvas must intersect at the principal vanishing point of the painting. That's just how our eyes work. Lines that are parallel in the actual scene but not perpendicular to the canvas intersect at their own vanishing point called the horizon line. All right, so we have the principal vanishing point, which kind of establishes our entire horizon line, where there may be other vanishing points, not necessarily the principal one. So let's look at a couple of artworks using perspective. Leonardo da Vinci, not just a Ninja Turtle, but actually a fantastic artist, in 1452 to 1519, contributed greatly to the science of perspective. We can see da Vinci's mastery of perspective in many of his paintings, but the most obvious one is The Last Supper. You will notice several parallel lines in the actual scene intersecting at the principal vanishing point of the painting, which is directly behind the central figure of Christ. So we see that the eye is drawn by everything, right? All of these parallel lines, all of these lines coming together, we have our vanishing point figured right over the Christ figure. I don't have any other word for him. Everything, right? Table's edge, the edge of whatever this is, everything headed towards the vanishing point. The German artist Albrecht Dürer, 1471 to 1528, so he was a contemporary of Da Vinci. Almost assuredly, they were kind of known to each other. He further developed the science of perspective. I don't know how much further since they were the same age, but they worked on it together. The next slide, we're going to show one of Dürer's woodcuts showing an artist using his principles of perspective. Now remember, the next slide is the art. So it's not like a drawing of what was happening. Well, it is, but the drawing of what's happening is the artwork itself, right? A string from a point on the lute is attached to the wall at the point corresponding to the artist's eye. At the point where the string passes through the frame, a point is placed on the canvas. As the string is moved to different points on the lute, a drawing of the lute is created in perfect perspective on the canvas. Now, a lute is a kind of a pear-shaped, I don't know, Musical instrument. All right, so here we have the artist's eye for the canvas attached to the wall. And as we move to different points around the lute, points are made, or these values are put onto the canvas as the string intersects the frame. Woo! That was rough, but that's exactly what's going on. And this was all in wood. This is a wood cut, a wood carving from 1530. Crazy, which is weird because that just said he died in 1528. Maybe 1530 was when it was released. That was definitely Albrecht Dürer's insignia, though, indicating it was his work. Now, symmetry refers to a kind of balance or a repetition of patterns. In mathematics, symmetry is a property of an object that remains unchanged under certain operations. So we might have reflection symmetry. An object remains unchanged when reflected across a straight line. Think of this blue dotted line as a mirror. The left side of a capital A looks exactly like the right side of a capital A. Similarly, the left side of a capital H looks exactly the same as the right side of a capital H. But H also has top to bottom symmetry. If we look at a letter like E, we do not have any vertical symmetries, but if we were to put a dotted line through here, we do have top to bottom symmetry on the capital letter E. Rotational symmetry, an object remains unchanged when rotated through some angle about a point. A 0 or an O, right, we can rotate it 360 full degrees any step along the way, it's going to be an O. S, let me see, what happens if we flip this upside down? Well, this part comes back up here. We would say that this has 180 degree rotational symmetry because it will take an entire flip upside down to get it back to the same place. Translation symmetry, a pattern remains the same when shifted to the right or to the left, right? X is just going to be X, it just looks the same. So in finding symmetries, we can identify the types of symmetries in a star. The 5-pointed star has 5 lines about which it could be reflected, right? One that goes through each point and then like that. So there are 1, 2, 3, 4, 5 of those, right? 5 different ones of those. It'd be reflected without changing its appearance. 5 reflection symmetries. But it has 5 vertices that all look the same. It can be rotated, right? I could rotate this one down here. Everything just gets rotated. And I can rotate it once, twice, 3 times, 4 times. 5 times makes a whole. So 1/5 of a circle, which is 72 degrees, and it still looks the same. We could any multiple of 72 degrees, right? So 72, 144, 216, 288, back to 360. A star is just going to be a star. So we have 4 rotational symmetries, 4 different places that this tip can end up, and 5 different reflection symmetries. A star's pretty cool. A tiling or tessellation is an arrangement of polygons that interlocked perfectly without overlapping. And they interlock perfectly. No gaps, nothing like that. Notice these triangles are all uniform. They're all there on purpose. So tilings, this will be one of the projects that you'll be able to do for the fall 2023 class. Some tilings actually use irregular polygons. Tilings that have are periodic have a pattern that's repeated, right? Just like repeating fractions are periodic. Aperiodic tilings do not have a pattern that's repeated. And we can create a tiling in really any way. If we do this by translating the quadrilateral shown, we want to make sure that we don't have any gaps. Like if I move this in a downward direction, right? I'm going to slide it translational symmetry. I don't want... Ooh, the mailman's here. We can't have this gap. That's a problem, right? I would have to put tip to tip in order to slide these around. So no gaps left behind. We can find the solution by trial and error. Having a pattern block that you're drawing on another page is the best way to do this. and translating the quadrilateral in different directions until we have correctly shaped gaps. Here's one solution. All right, maybe I take this quadrilateral and instead of sliding it the way I did, maybe we slide it along a different line. Note that the translations are along the directions of the two diagonals of the quadrilateral. The gaps between, also quadrilaterals, right? Four lines. And they interlock perfectly, so we now have two different images, and it looks like it's kind of a version, but it's a different version, like the black and the white version from a negative. That's it for math and art. Thank you very much for listening.